Okay, yeah, welcome back from the lunch break. Lorenzo Orecchia is going to talk again about the continuous methods, and as I know for sure, he has plenty of experience educating ignorant office mates, so I'm glad he's giving his second talk. And
Thank you, Thomas. Okay, so let me start with asking if there are any questions that came up over lunch about any of the material you saw so far. Because from now on, we are going to meander a bit more, and so I just wanted to make sure people were comfortable. Okay. All right, so remember that the last thing we managed to essentially go through the analysis of what I call the primal averaging, of which an example is this Frank-Wolfe method. So I wanted to clarify that what the result you actually showed is more general than Frank-Wolfe. It applies to any case in which you have this smooth property on your gradient map and your non-smooth property on the mirror map. So it's more general than Frank-Wolfe. And the next thing I wanted to do was to move before we move on to the kind of the next case, which is non-smooth gradient and a smooth mirror map. I wanted to give you a bit more of kind of a pictorial intuition of what this means in practice for gradient methods. So you should really think of primal averaging and Frank-Wolfe as a proxy for gradient descent. So the one method that I haven't really talked about in this talk is kind of unconstrained gradient descent, where you just walk towards the gradient. And the reason I haven't talked about it is because it's kind of special. It's hard to present it in this framework. You can, because there is no real set. It's not easy to define what are the points you're taking a convex combination of, because you're unconstrained. Okay? So as a matter of fact, the way to think about unconstrained gradient descent is that in some sense, you are constructing a very large ball around your points, and you're picking points on the boundary of this very large ball that is guaranteed to include your optimum, and those are the points that you're taking a convex combination of. But even then, there are a couple of details in that construction that make it messy, and that's why I decided to present Frank-Wolfe instead, for which we have a much nicer understanding. But a lot of what the intuition that I'm going to say about primal averaging and Frank-Wolfe will also apply to unconstrained gradient descent. And the point I want to make is essentially this, that we saw that the way Frank-Wolfe or more primal averaging works is that it's focusing on the function. It's really looking at the function value at x bar, so the function value at the current primal point, and that is the part of the problem that's smooth, and that's the part of the problem where the algorithm really moves in the direction of the gradient and tries to make progress. And that's borne out in practice, because what happens when you do gradient descent is that you're going to query a point, get a gradient, and together with your gradient, you're gonna query a point, you're gonna move to a point that decreases the function value, and you're gonna get a gradient that gives you a lower bound. But what happens when you do? Oh, so I should have stopped the slides. Sorry. What happens when you do gradient descent in practice is that gradient descent really wants to decrease the function value, but it's not caring too much about the lower bound. Because on the lower bound side, like as we saw, it's really just maintaining this average of lower bounds. So in practice, what happens is that this lower bound increases very slowly. And these two issues are related because gradient descent, in some sense, is focusing a lot on decreasing the function value and not as much as increasing the lower bound. In the case when your mirror map is also smooth, you can do better. So in the case, say, you just have both your function and your mirror map are smooth, then there is a better thing you can do, which is what I call a dual averaging update. And the reason is, if you want to reduce the duality gap, you could take another gradient step here that decreases the function value, but intuitively something you can do to improve your lower bound is take a longer step, which might overshoot the optimum. But if you overshoot, you get a gradient that points in the opposite direction. Okay? And that's very nice for the lower bound, because now, suppose I take a convex combination of this gradient and this gradient, then I get this gradient. And this is a very nice lower bound. Okay? So in general, in practice, depending, there are implementation issues here, but like a theoretically like a implementation of these algorithms that's faithful to the theoretical algorithm will show you that the dual averaging updates in general tend to overshoot the gradient descent, while the gradient descent tries to make smaller steps because it doesn't want to increase the function value. And now, if you remember this picture I showed you at the very beginning of this talk, I wanted to, okay. That's exactly what's happening in this picture. That this gradient descent is just trying to decrease the function value. This guy, it's okay with overshooting, because when it overshoots, it's getting a gradient that he can use to improve the dual solution a lot. So in some sense, I hope this gets some intuition about these momentum methods. Like, why would you want to keep going? Why would you want to overshoot? And the reason is that by overshooting, you're making dual progress. All right, so this is kind of a bit of intuition, which I find useful. Okay. So let's get back to the next method we want to look at. It's really very similar to what you just saw. Is that say that things are happening in the dual now. So this is a method where your f is non-smooth, but your psi is strongly concave. So you can think about minus psi is strongly convex. And then what this tells you is that this forward map is non-smooth, but this backward map is smooth now. This is a case where this may not be a gradient, this may be a subgradient now, because this function being non-smooth, in principle, it might not be differentiable. And sometimes there is a way of, that I'm not gonna talk about today, but feel free to ask me offline, in which this can be related to proximal operators, and I'm not gonna go into it today. All right. So I mentioned the properties. So an example of this is maybe a common problem you may want to do in a statistical setting is you want to do entropy maximization under some linear constraints. Okay? So then your linear constraints would be encoded in this non-smooth part. And then entropy is a strongly concave function with respect to the L1 norm. You can check this. So it would fit exactly this kind of frame. Okay. So, and again, what's going to happen here is very similar to what we saw before. The only smooth component in this picture is this mirror map. So the only place in which I'm going to use my current dual solution, Z bar, is in the definition of the lower bound. Everything else here, my upper bound and my other lower bound term, everything is an average. smooth, and this is loser bound. Okay, and I'm not going to go much into detail because if you think about it, everything I saw for primal averaging applies exactly to this case. This is exactly the same primal averaging where I flipped primal and dual. It's exactly the same picture. So what's happening is that instead of having, remember that for primal averaging, I would evaluate the gradient of f at x bar and map it to ZT. Here things are flipped. So what's happening is that I am taking my current dual solution. I'm using the mirror map to map it to a primal point. I'm disregarding my current primal solution. I'm only looking at kind of my instantaneous primal solution. And I'm mapping it back to the dual space. So you really think of it as gradient descent in the dual space, which is why it's called the mirror descent. And I'm going to go into one example, specific example of this later on. Here I just wanted to emphasize the symmetry. And so because this is the same as the primal, I'm going to move on, and I'm going to get to a more interesting case, which is the case in which we can achieve acceleration. We can get faster algorithm, and that the picture is that this map is smooth, and now this map is also smooth. Okay, so you can imagine what I'm going to say is that, so now, again, up in the upper bound, I know f is smooth, so that's the contribution of f. In the lower bound, I know the psi star is smooth, so that's the contribution of psi star. Everything else is an average. And right. So actually, I see. Apparently, I didn't have the derivation here. I want to show the derivation just to show it once more. So I claim that given this definition of upper bound and lower bound, if I enforce my invariant, I'm going to get this kind of dynamic. So let me tell you first about what's the dynamic, and then we can do the calculation on the whiteboard. So the dynamic is really what you would expect, in the sense that because now both the gradient of f and the gradient of psi star are smooth, you can apply both of them at this current solution. Okay? So now both x bar and z bar are involved in the dynamic. And that is what's behind acceleration. If you want to think about so if you want to develop some intuition, I recommend trying to think about zero-sum games in which X is the primal player and Z is in the dual player. And it's an interesting exercise to try to think about kind of what kind of strategies these different dynamics correspond to. Right, because I wanted to do the formulation. Let's see, I put it afterwards. Okay. All right, so when I differentiate, so now I'm going to show that, so I inverted the order of my slide. I'm going to show that this is actually the dynamic that we get from the gap invariant. So when I differentiate my gap, now I have two kinds of terms. I have the terms that come from the smooth part and the terms that come from the non-smooth part. Okay.
Sorry, you're in the case of both smooth.
Right. It's the case in which both are smooth, but remember that f star and psi are still non-smooth. Those are, because there are four terms. There is f, psi, f star, and psi star. So in this case, 2 of them are smooth and 2 are not smooth. It's actually a good question when everything is smooth, then you can recover this linearly convergent algorithm. So when the convergence is like log 1 over epsilon. Okay, so let me do this calculation on the board. Okay, so first step, so this is the derivative of my upper bound. Sorry, this is the derivative of my gap. It has these 2 terms, x bar dot and z bar dot. And so the way you go about eliminating those terms is that you use the fact that your x bar and your z bar are averages. So you get a simpler expression. So because are averages, then you're going to get alpha prime of tau f x bar t, and this alpha t plus 1 cancels with this, so you just get the gradient at x bar t xt minus x bar t. So that's the first row. You get something similar on the second row. Actually, writing on the board, let me skip all these t indices because they're very nice on the PowerPoint, but when you write, it's a bit cumbersome. Everything is at time t in any case. So then you get psi of z bar plus the gradient of psi star at z bar z minus z bar. And then these last 2 terms are just averages, are just function values. They are f star of z minus psi star of minus psi of x. Right. Okay, so we want this big expression to be 0. And the idea is again that we try to make it 0. We try to define things. We try to define our z and our x to form conjugate pairs, such that things cancel out. So let's see what we can do in this setting. So you can notice I have f of x bar here, and I have f star of z here. So it makes sense to make z and x bar be a conjugate pair. So the alpha t plus 1 cancelled out when I replaced the z bar and the x bar because of this. And that's convenient because now I just have this alpha prime kind of in front of everything. Right, so the first thing I'm going to do is I'm going to define z to be delta f of x bar. So that's going to take care of, it's going to make z and x bar a conjugate pair, and it means that this plus this is going to imply that f of x bar plus f star of z equals z x bar. And it's convenient because I actually have zx bar appears in my formula because this guy here is z and this is x bar. So what happens when I make this assignment, by virtue of this assignment, I get rid of this term, and then zx bar. So this term. Now I do exactly the same thing on the dual side. I have psi star of z bar, psi of x, so I make x and z bar a conjugate pair. And exactly the same reasoning means that I can get rid of this guy, and this guy. What I'm left with at the end, if I did things right, should just be alpha prime of t zx there was a minus here, and then minus zx. So this cancels, everything is 0. I just wanted to do this because this is what all these proofs in the end boil down to. You have some derivative of your gap, and you want to choose your z's and your x's to form these conjugate pairs to make things 0. So any questions about this derivation? We're going to do a similar one for a more interesting case soon. So I wanted to have this one down. Now it's time to go on the board. Okay. All right, so we have the dynamic. I want to talk a bit about the discretization of the accelerated dynamic. Discretization for acceleration is actually complicated. It's actually more complex. So I'm not going to go into the full detail, but there are a couple of very interesting ideas I want to sketch. So the first point is that Forward-Euler, this nice simple scheme I've shown you for primal averaging, so Forward-Euler doesn't work. If you just do Forward-Euler, you get, this only gives you a bound that looks like L d squared over t, which is the same as for primal averaging. So Forward-Euler doesn't let you improve the convergence. And how do you overcome this? And what's nice about acceleration is that there are two ways to use discretization to overcome this problem. So there is one approach I like to call Nesterov trick. Which gives rise to what people call accelerated gradient descent. The Nesterov trick is the following. You do Forward-Euler. So what happens when you do Forward-Euler, you are at some point, say, actually you can work in configuration space. So when I write a point, it's not only a primal point, it's a primal and a dual point. I do Forward-Euler, and I get to my new point. And unfortunately, I still have too much discretization error. And then Nesterov has this idea that the actual gradient of f is pointing in a different direction. And because f is smooth, I know that I can take a little step in the direction and improve my function value. So what Nesterov does, he says, I'm not just going to move to this point, I'm also going to take a little gradient step, come to this point y z bar, the dual part is left the same. And now the next thing this says is it uses convexity to argue that if I now take a combination of these 2 points, a combination that is closer to this side, the gain I make from this gradient step exactly matches the discretization error. And so I can obtain, I can actually match the kind of gap that we saw before for just a continuous method, which was G0 over T squared. So that's, I just want to give you a kind of pictorial idea of what it has. The calculation is not too hard. So the idea, the point about this is that it's kind of, I mean, I don't have a good systematic interpretation of what this is. It's a good ad hoc trick for when you have smoothness. Because smoothness guarantees that because the gradient is changing slowly, you can always make a little step that improve your function. So this is what's called Nesterov, what I think of as Nesterov trick. Then there is a more, there's a kind of a slightly more systematic approach. Okay, so if I call this Nesterov trick, I have to call this Nemirovsky's trick, right? But this is not really a trick. It's more. And so here the idea is that it's the following. So we have an integral. You know, as we said, we are trying to discretize the integral of the gap between t and t plus 1. So this green function here is d dt alpha t plus 1 gt. So that's my invariant. So I'm trying to discretize this guy. And Forward-Euler just takes this, uses this approximation. And one way to think about what Nemirovsky does is that it's something more similar to what people call the midpoint rule in numerical integration. So the way it works is that you are again at x bar, z bar. Can we turn off the one? Thank you.
Go to the right.
Sorry?
Go to the right too.
Yeah, but I don't know. I like to be near it. I feel emotional about it. Okay. So Nemirovsky's idea is this. I have x bar, z bar. I'm going to take kind of a smaller Forward-Euler step, where the step length is half of what it should be. I get to this x hat, I get to a point x hat z hat, and now I use this point to estimate the gradient of my function. So I take this gradient here, so the gradient of my dynamics at this point, and I apply it at my original point. And this is, I use this. This is my next point.
Sorry, x hat, z hat is chosen using Forward-Euler by half step.
Yeah, it's an extrapolation step. So I'm just, because the idea is that I really would like to estimate what the gradient looks like in the middle of this interval at t plus a half. I would like to take this guy and then use, right, use maybe this approximation for the integral. And so how can I access this point? I need to kind of simulate what the evolution would look like for half a step length. And then I use this point and the gradient and the derivative of my dynamic at this point as a proxy for this. So that achieves also, again, you get the same bound. So you get the GT goes down as a G0 over T squared.
Wait, so when you say this is Nemirovsky's trick, is this supposed to be the same as mirror prox?
Yes.
Wait, so for the actual standard mirror prox, this there's not a 1/2, right? You're actually using a full step.
Right. So there are different ways of doing it. Yeah, you're right. So. Yeah, I'm slightly cheating here, but.
Okay. I mean, do you know? Can you actually analyze this method?
Yes,
It would still work. You make it a factor of 2 in the convergence bound. But
Okay.
yeah, if you work out it. We can talk later.
Yes.
So there are variations of this you can do. This step length can be different, but in principle, you can think about this intuition. There is also a different intuition of what this method does, which comes from something called backward Euler. Do people know what backward Euler is? Okay, so the idea is this. So in one line, backward Euler would be the way of approximating integral, where instead of taking this line or this line, you take the gradient at the end point of your interval. This seems easy enough, but there is a catch, which is you are doing an evolution, right? So you are at x bar, z bar, and you're following some dynamic. So the differential of this is some function. Let's call it time evolution at x bar, z bar. And so what you're trying to, when you do forward Euler, your step follows the time evolution at x bar, z bar. So this is forward Euler. When you do backward Euler, you have a more complicated task. What you want to find is you want to find a point, x bar prime, z bar prime, such that the gradient at this point, so this is the time evolution at x bar prime, z bar prime, when you apply it in a negative direction, takes you back to x bar, z bar. Okay? So here, when you do forward Euler, you take the gradient at your current point. When you do backward Euler, this is also called implicit. It's an implicit method, because there is no, you need to find this point x prime, z prime, which has this property. The property that the gradient of the time evolution at that point takes you back to the original point.
Dynamics are not time reversible.
I don't know. Yeah, probably not. I would guess.
For optimization,
They shouldn't be, right? Okay, so this is the idea. So and this method is explicit. So implicit methods, if I was able to do exact backward Euler, I would actually have no discretization error. But it turns out that this task inside backward Euler is hard to compute. It's hard to find a point, because you don't know what the gradient at the point will be. So what Nemirovsky is trying to do is, in some sense, you can think of it as trying to approximate this backward Euler step. And this can be made more formal. Turns out that there is a natural iterative way to approximate backward Euler, and this step that Nemirovsky is doing is the first step in this iterative way to approximate backward Euler. I already went too much into the detail. So here I wanted to mention a number of I think, conceptual questions that I find interesting. First, it's not really clear if this, to me at least, whether this is a better idea than this one, both in practice and in theory. There are a bunch of open questions about what happens when these gradients you get, the gradient of f, is noisy. And then the choice of discretization may have an impact in the way the noise affects you. So there is an interesting question about if you have Gaussian noise on top of your gradient oracles, it is relevant for differential privacy. It's not clear if this method and this method have the same performance. And then, as we talk about open questions in recent developments, there is a lot of work going on in trying to figure out if there are different ways of discretizing these dynamics that are better for specific problems. Let me mention one example. A very important direction is trying to understand what other notions of smoothness you can use in your discretization. So we have, for example, a result that applies to positive linear programs. So these are linear programs where say a packing LP, so you want to maximize 1 transpose x such that A of x is less than 1. And what does it mean that it's a positive LP? It's because I tell you that all the entries of this matrix A are non-negative. So now, if I use these methods out of the box, the best I could do would be, so the running time to get to an epsilon approximation would be something like okay. And this is essentially achieved by doing something called smoothing plus this Nesterov algorithm. And it's very surprising that we can exploit the fact that this is non-negative to do a different discretization. And this discretization gives you a running time which is independent of the size of this is the number of iterations. The number of iterations that's independent of the numbers of the size of the entries of A. So this result doesn't work when the matrix, your constraint matrix, is general, but somehow something in the fact that this is non-negative, together with the choice of dynamics that we do, which is actually it's the same choice of dynamic as this, but we have a different discretization that allows you to get a much better behavior. I don't really understand what this is, beyond this problem, but it shows that there are, I think, interesting avenues to research there. Mhm.
Are those the same notions of error in each case?
Yes, they are one, because there is no square here, right? So these are 1 plus epsilon multiplicative approximation. So it's a different notion of error from the additive approximation we have been using so far. It's a 1 plus epsilon multiplicative approximation.
Doesn't first
Why should it
expression
depend on-
not type check then?
Yeah.
Because if I just double the whole matrix A,
Mhm.
it doesn't change what multiplicative error means. Or if I have the whole matrix A, it doesn't change what multiplicative error means, but it has your math. So that's
Uh,
There's scaling between the Churchill convention drug.
sorry?
The scaling of your problem is already rescaled, right?
Right. There is some condition on the scaling, you're right.
Because this is where it's not really so this is already after scaling you have the...
Yeah, there is a condition about the scaling of A is fixed. I think something like the mean L infinity norm of a column of A is 1 or something like that. There is some fixed scaling. Right. Okay. Okay, so I think that's, I just wanted to give you a rough idea of interesting directions in discretizations. Also, Jonah Sherman, he just talked now. He has a recent paper where he does some very cool stuff, different kind of way of discretizing, different conditions, different notion of smoothness in some sense that you can use to get a better discretization out of backward Euler. So I really like this area of research in terms of finding problem-specific discretizations of this dynamic. And one might ask, why haven't people done this before, right? So these discretization schemes have been known since Euler, like the name suggests. And I think my explanation is that people that knew this, people in convex optimization, are interested in more general problem classes. So the kind of problem classes they work with, smooth, strong, convex composite, don't have enough structure that you can really go and play at this granular level with discretization. But once you get into the TCS community, we're interested in solving problems that have a lot of structure, like mass flow. There is a graph structure. There is no negativity. There could be a matroid structure. There is all kind of stuff where we can really exploit that in the discretization. And so I think it would be a great, thing to think about in the context of a program like this one, where we are trying to bridge continuous and discrete.
Had you not, for the Poisson LP, had you not used accelerated gradient descent, what would be the exponent of epsilon? Is it epsilon squared?
Right.
Can you repeat the question, please?
Yeah, the question was, if I had not used AGD in this iterative solution of this LP, this exponent would have been squared. This you can still keep as it is. There's a little trick there.
Infinity, you just mean the largest entry.
Largest entry, yeah. The largest entry of the matrix. So 1 to infinity, I guess. Okay, so in the last 10 minutes, let me do something important, which is talk about non-smooth optimization. Because, I covered all these 3 cases in my slides, where one of each components was smooth, but a lot of the problems that we are interested in, especially in discrete optimizations, have relaxations which are non-smooth. Like this guy, nothing is smooth here. Okay, so how do we deal with this? And here there is a great trick that, a great technique that I want to show you. And I'm planning to talk more about this. We'll have a workshop on fast iterative methods, and I think we'll hear more about this. But let me give you the basic idea. So a lot of the problems, like as I said, you just have a mean of f of x. Maybe inside some closed, take a compact convex set. There is no psi. So far we have worked in this world where we have this nice psi, this mirror map that comes in the objective. But if my problem doesn't come with psi, what am I going to do? And so here the nice trick is that you're going to build your own psi. Okay? So in some sense, you're going to add a psi here. And of course, you want to build it such that, so what do you want of the psi? You want delta psi star to be computable. And because you are at it, you probably also want it to be smooth, you want psi star to be smooth. So you can actually use it effectively. If you just do this, then you've really changed the optimization problem a lot. Okay? You're optimizing something different. But there is a trick now that if you think about it, say our upper bound, can do this for the lower bound as well, is a function of time in this method. So what I could do is I could think of working in I can make the terms in my upper bound also depend on time. So what would my upper bound be? I could use, so because f is not smooth, I need to use the average, I need to use average on the upper bound. So f of x 0 plus the integral. But then, on this term, because on this term, so what's going to happen is that I'm going to add a weight of 1 over alpha t plus 1 on this term. So I'm going to scale it down with time. Actually, let me do it in a better way. Remember, this is my invariant. So now my invariant is going to be an average. Let me skip some of the details. Let me just write an average of the f's, because the f's are not smooth. An average of the this is not here. And here this term is still going to have an alpha t plus 1 in it. This is my this is the upper bound, and then the lower bound is going to look like I star of t minus so let me explain. Can we turn on the screen again? So, can we turn on the projector again? So if you notice, when we did this business for composite optimization, whenever I had an average, it was not scaled in the expression for the gap. So see, inside this bracket, this is an expression, this is part of the gap. And the average, because I multiplied by alpha here, this average is just there. What's happening now is that because I introduced this scaling here, the terms that depend on psi are all divided, are all scaled down by are all scaled down by alpha t. So what's happening in some sense is that at time t, I'm optimizing kind of a different function at each time t, and the function I'm optimizing at time t is this function, where the weight of my mirror map depends on time. As alpha becomes large, this becomes negligible. Okay? So what this allows me to do is choose, and I can introduce my own psi and use it in the algorithm as I would do in composite optimization. You can do the same kind of calculation as I did before to figure out what the dynamic is. The dynamic is the same as we saw in dual averaging, except that there is an extra scaling here. It's easy to deal with. And what you get is a way of functionally, what this does is really you are creating a smoother version of f at each time t. So there is a way of interpreting all of this as smoothing the function f. Another way to think about this transformation is what people call, figured this out recently, what people in optimization call homotopy. So the idea behind homotopy is that, at time t, in the beginning, your function is just going to be f minus psi. So at time t0, you're optimizing this function. Then as time progresses, your function changes and f becomes more important until you get to a function which is essentially f. And this kind of continuous transformation from this function here, which maybe was an easy function, to this function here, which is a highly non-smooth function, is what they call homotopy. And it also can be related to preconditioning. So the point is, if you have a non-smooth function, you can introduce a psi that depends on time and have this nice transition from an easy problem to a hard one. And so lots of these techniques that you might have seen, like multiplicative weight updates for non-smooth optimization, are doing this. I'm happy to talk about that offline. What that means is that the existence of this attack, this way of dealing with non-smooth optimization by building your own psi, is very interesting because it brings a different weapon to the game. It brings the possibility, you get you get to design your own psi. And different psis have different properties. So a very nice also area of research is what is the right psi. Also, this is also called the regularizer. What is the right regularizer for a given non-smooth problem? And here I have also lots of examples. People want to talk to me. I'm thinking about it.
Okay. Okay, thanks, Lorenzo. Questions?
Could you quickly say why do you think of exponential rates as homotopy method?
Could you repeat the question?
So the question was, how do I think of multiplicative weight updates as an instantiation of this homotopy method? And the idea is this, that when you do weight updates, say that you're actually just doing it for online learning. So in the online learning setting, you have some cumulative, this is your cumulative loss vector. This is the sum of the losses you've seen so far. The way you define your weight update, the way you define your point, is you look at the argmin of, you want to have a point that does well against all the losses you've seen so far, plus some regularizer. And this could be the entropy. Okay. So this will give you multiplicative weight updates, because if this is the entropy and x is on the simplex, the solution, what you get from xt is e to the minus lt over the sum of I and the sum. So this is multiplicative weight updates. How is this homotopy? Well, it's homotopy because you're really scaling by alpha t. So as t goes on, this term, which comes from your function, is increasing in weight, and this term is fixed. So actually, if you apply this homotopy method for a non-smooth function, you get exactly something like this. So the key in these weight updates is that the contribution of your regularizer is staying fixed through iterations, while the contribution of the function is increasing.
Other questions? Okay, then thanks again, and we'll have a half an hour break.